I'm starting.
So hello, this is Team UMaT from Ghana, and we are privileged to participate in this year's robotics competition. My name is Joel Mensah, and I have a petroleum engineering background, and I happen to be the team lead with Professor Richard Amorin, who is the faculty advisor.
My name is Precious Sigo, and I have a petroleum engineering background, and I contributed to the design of the work plan for the project.
My name is Aaron Antuyin with electrical and electronics engineering background, and I contributed to the graphical user interface, the work plan, and the RSS for this project.
My name is J. Fiyoso, and I studied petroleum engineering, and I contributed to the document design for the project.
My name is Joel Edwoku. I studied petroleum engineering, and I helped in building the RSS system.
Aaron Delapo is my name, a computer science and engineering student. I contributed in the development and design of the GUI, graphical user interface.
So this is going to be the outline of the presentation. We are going to look at the overview of the final system design, and in doing that, we are going to look at the work plan design, the drawstring, the steering system, the user interface, and finally, we are going to discuss the total cost that was incurred during the project. So the flow of the system involves first generating the work plan, and secondly, designing the drawstring, and thirdly, steering the wall to hit the target.
In designing of the work plan, we use two main interpolation techniques, which is the Akima 1D and P-chip interpolation. So with the Akima 1D interpolation, is used to calculate the derivative at a given data point, while the P-chip interpolation is used to construct smooth monotonic curves passing through the given data point. So upon conducting our research, we realized that the P-chip mostly outperforms Akima 1D in constructing most well paths. So we illustrated that by selecting some few 4 targets, and with the first graph, we can see it. There we can see that the curve was smooth till it reaches the last target using the P-chip interpolation. And with the second graph, we can see the Akima 1D. After the kickoff point, the curve protruded before continuing to the last target. And we can adjust that by restarting the start coordinates by 150, -50, and 0 to be the same as the P-chip interpolation.
This is the flowchart for the work plan design. So you start by inputting the target coordinates and the geological data. And once that has been inputted, you adjust your parameters such as the kickoff point and the formation to build. And once that is done, you click on run. Now, if the QOP was adjusted, that's the user decided to choose a QOP, then it moves straight to generating the coordinates from the start to the kickoff point. But if the QOP wasn't adjusted, in other words, if the QOP wasn't selected, the program automatically determines a QOP, then generates coordinates from start to QOP to construct the vertical section of the wall. After that, it interpolates coordinates from the QOP to the last target to produce the curve section. And getting the vertical and curve section, we calculate the dog leg inclination, the azimuth, the measured depth, dog leg severity along the wall.
For our drawstring design, we decided to design our draw colors and then design our draw paths
So these are the mathematical models they use in designing our drawstring. We use the fast-state vacuum equation. We use this particular torque and drag equation. And then this was used to calculate the length of jaw pellets. We are using a slick BHA, so we want to design our jaw pellets as well. So this is the vacuum flow process for one particular drawstring. So we start our program. Then we've created an API sheet which has several drawstrings with their properties such as their ID, their OD, their grade, and then their weight. So we normalize the drawstring objects using that particular sheet. And then it calculates for the parameters such as the backline force, the passive backline force, and the moments of inertia for each particular drawstring in the API sheet. It then later checks if the string buckles or not. So if buckling occurs, it outputs it. If there is no buckling, it shows. So these are the conditions for which buckling works. So if the FB is less than FP, that means no buckling occurs. If not, it's either a lateral or helical buckling. But our main attention was on the first condition, that whether buckling occurs or not. So in designing our jaw pellets, we take into consideration our bit properties and affirmation characteristics. This helps us to determine the joining parameters we want. That's the maximum weight on it to allow us to design our optimal assembly. We decided to test for if our BHA will buckle or not. So if the BHA buckles, it redesigns another BHA. If there is no buckling, it maintains that BHA, and that particular BHA is used in the simulation process. So for our jaw pipe selection, the idea was to create and then select a particular pipe with the minimum torque and drag values and with the least tendency to buckle. So we started by normalizing our torque and drag values for each jaw pipe along every service station per the API sheet we had. We then applied weight factors to our torque and drag and in our buckling. But in this, we applied more weight to our buckling because it was a condition we considered more. We then found the average score for torque, drag, and buckling for each jaw pipe in our API sheet. We then found the total score of each pipe using the same condition, that's a torque, drag, and buckling. We then sorted these jaw pipes in order of performance. So the output is, it gives a list of jaw pipe, either top 10, and the user has the opportunity to select the best out of the list to be used in the simulation process. The user can also override the system decision by selecting any of the pipes sorted to be used. This system is done autonomously.
So for the steering system, what we did is we modeled the RSS that the rotary steering was. So in one major feature, one major thing we looked at in the RSS was how to post navigation with horizontal plane. So what we did was that we modeled the RSS in such a way that it has three parts around it that are responsible for posting this deviation. But for the vertical deviation, that was we made use of the base model that was provided by robotics. So a basic flow of how the RSS works to get a particular the best coordinate from one particular station to another. Say we are at station 1, we want to move towards target 1. How do we get towards target? Like how do we move towards target 1 to make sure that we hit it? So this is a basic flow chart showing that. So first, what it happens that the RSS has some methods within it that initializes various variables and parameters that it needs. So at every station, the RSS system will need to know things like deformation, aggressiveness, the CCS, the weight on bit and other parameters at that particular station, so that it will know the appropriate rate of penetration or the appropriate mass, the appropriate force that is supposed to use in causing the steering. So for the vertical section, like that's for the z-axis, how the RSS is able to get those coordinates is that we make use of the bit model provided by robotics. So this bit model we used to calculate our top on bit ROP. I mean the ROP Excel. So for the ROP Excel, we use that one in getting our z coordinates. Yeah, so we use the ROP Excel from the bit model and getting the Z coordinate. But for the XY coordinate, as I said, we're able to achieve that through the paths that we have, because that talks about the deviation that the RSS has to cause after the kickoff point. So what happens is that let's say we get to the kickoff point, then we want to start posting the deviation. The RSS takes the work and then looks at it. Yeah, currently we are at this particular position, but then we want to move towards this particular the next position. Let's say, which is let's say some 10 meters away to the next station. So it sets the current one to be the current position, sets our target position to be where we want to go to. Then it gets the XY coordinates that will move us more towards that particular target coordinate. And how does it get the XY coordinates? That depends on the amount of force that each part around the RSS is able to produce. So say we have a part at the left side of the RSS. This part is being extended to a maximum or to some particular magnitude of force. What happens is that the extension of the part is supposed to hit against the formation, which will push you towards the right. So we extend the part at the left to move towards the right. We extend the part at the right to move towards the left. Just taking these two things as an example. So there's an algorithm that the RSS goes through to set the appropriate forces for these three parts. As I said, the parts are evenly spaced around the RSS. So the algorithm sets the appropriate force that's supposed to be around these three parts in order to move us more towards the particular target that we set. So after getting the XY coordinates that are appropriate, it takes the Z coordinate that it got from the ROP that you got from the bit model that was provided. So after getting the XY coordinates, then it calculates the change in the measured depth. After that, it saves these coordinates, the XY coordinates, it saves the ROP Excel that was put in, it saves the torque on bits, the weight on bits, and also the measured depth that it is calculated. So these particular parameters are what is stored at every station. So every point that the RSS is going to generate will contain data, including all this. That's the MD, weight on bit, torque on bit, ROP Excel, and all the coordinates. So with this particular class, what it does is that it deals the coordinates. It doesn't generate all the coordinates at once. So after it has calculated the particular coordinates for this part, it yields them. That means that it returns these coordinates to whatever function is calling it. So it will not calculate the next one. It will wait till the function calls it again before it's able to calculate the next one. This was the way we used to improve efficiency and make sure that we don't store a lot of data that will cause some troubles. So after we've figured the coordinates and let's say we call upon the RSS to get us the next coordinates, it wouldn't just go ahead to try to calculate or to try to stare. What it does is that it looks at the previous coordinates that we generated, the Z coordinates of those coordinates or the Z axis of those coordinates. Is it less than the Z axis or the Z coordinates of the last target we are supposed to get to? Because if the Z coordinate of the last one we generated is greater than or let's say is equal to the Z axis of the last target that we have in our system, that means that we've gotten to the last target and we need to continue the simulation. So if it's less, what is going to happen is that to go back to set a new target based on the work profile, then continue this process to generate new coordinates and data. If it happens to be equal to or greater than, then it stops, and that will be the end of the simulation. So this is basically an overview of how the RSS goes through to generate coordinates from one station to another.
So on steering a bit, we consider the formation aggressiveness, the CCS, the side cutting factor. And from that, we generated the weight on bits, which we had 50,000 pounds. And the RPM of 130 rev per minute, with a drilling efficiency of 0.35. So based on these parameters, we could steer the bits having a minimum deviation and a high accuracy based on the each survey stations with the target points. So we used an interval of 10 feet for each survey station to get an accurate well path.
So about the graphical user interface, It's actually web-based, making it hybrid. And we did all using Python programming language. So it allows the user to make entries in form of a file or numbers. And it also has interactive sliders for change and range allocation. So it's built in a way that it is real time. That is, any slight change that is made in the inputs affects the output in real time. And also, simulation has controls so that it can be manipulated at every instance the user wants to. And also, it is user friendly. Taking in the rules of HCI, it's very, very accessible and clear, with symbols being clear to view, buttons nice, and it also allows and gives information of every single step in the system.
Because of the project, the team had to return to campus to continue with the project. And this was what was incurred during the 1-month stay. So in terms of accommodation, approximately $2 was spent each day for each member. And for the 30 days that was spent, it resulted in $60 per member. And translating that to 5 members, a total of $300 was spent on accommodation. And $4 per day was disbursed to each member for the purposes of getting food. And for a month, it costs $120 for each member. So translating it for the 5 members resulted to a total cost of $600 on food. And an amount of $80 was used to purchase snacks, that is tea, coffee, and biscuit for the tea, to sip and to chew while performing the project. And also an amount of $100 was spent on internet during the course of the project. And the total expenditure for that particular month was $1,080. And this was the cost for just the month of staying. However, within the course of the project, other costs were also incurred along the line. Thank you very much.